I'm Mohsen. I'm a postdoc at University of Toronto. I'll be speaking about quantum algorithms. The rest of this title is a short description of my history working on this area for the past 5 to 6 years. I started working on quantum algorithms for fault-tolerant quantum computers, and then recently I'm involved for algorithm for near-term quantum computers as well. Feel free to ask any question during the presentation if you have any. So for the, I guess this is not working. Okay, great. So for the first part of my talk, I'll be talking about quantum algorithms for simulating quantum field theories. Before describing the quantum algorithms, let me explain what a quantum field theory is. And let's start simply by what a field is. Field is a function that returns a value in space-time. The value is related to some physical parameters. The value could be a scalar, which, for example, it would be a temperature in this room. It could be a vector value, which is one example is the electromagnetic field, which is a vector field. The value could change over time, and the field theory is a mathematical description that tells how the value of this field is changing over time. There are some restrictions on the way that the field is changing. So all restrictions is within the Hamiltonian or the field theory that describes this evolution of the field over time. So quantum field theories is a case that we have superpositions of the fields at any time, like quantum mechanics that describes a particle. The particle could be in superposition of all possible states. Quantum field is describing the case that the field is in the superposition of all its possible values. Any field can have a particle, which would be excitations over the field. And these particles are represented like by bump on the field. If the bump is small and high, it's represent a particle with a high momentum, and if it's small, it represents a particle with a smaller momentum. And what we are interested in quantum field theories or field theory is like the scattering of these particles, and look at what would be the outgoing particle after the scattering process. We could have fields that coexist together, and each of these fields have their own particles. And if you look at the different fields that is in the nature, we will have this standard model of particle physics, which describes different particles for each of the fields that exist in the nature. I'll be specifically focusing on the simplest quantum field theory that we can describe. It's a scalar 5-4 theory, which describes the Higgs boson. It's given by this Hamiltonian. The Hamiltonian has a free part and interacting part. The free part is just a quadratic term, which could be like, you can think of it as a bunch of connected harmonic oscillators. And the interaction is a nonlinear term, which is the 5^4, and the name is coming from that. This is not a toy field theory, although it's the simplest field theory. It describes the Higgs boson in this table. So before going to tell you how we simulate a quantum field theory, let me tell you why we need to simulate a quantum field theory. At the end, a field theory is a theory, so we need to verify it by the experiments. And if it's a good theory, it should be verified whatever the experiment is telling us. So to do the experiment, this is a large hard-line collider. It's the largest physics experiment in the world. So in order to to verify the results of a quantum field theory, this kind of experiment, which is very expensive to run, tells us whether the field theory is consistent with the experiment or not. So it's kind of verification of field theory. So simulation is another way of verification. And also we see this kind of funny things that the physics paper coming out of this colliders have so many authors, many people involved in in like this, doing this experiment in order to verify the results of a quantum field theory. So in order to simulation, what we do is firstly we go to classical methods. For the classical methods, like the one method is using the Feynman diagrams, which are these Feynman diagrams that are used to do some calculation. It simplifies some calculations, but it only applies for big coupling field theory. It also breaks down in high precisions. So these are not useful for any type of quantum field theory that we are interested. An alternative method is lattice quantum field theories. These methods apply for they are good for static quantities, and they have like high precision for calculating them, up to 12 bits of precision. Some of them calculate, some of the quantities are calculated with this high precision using this method, but they are not useful for studying this the dynamics of the theory or the system that we have. So the question that we have is, can we efficiently simulate quantum field theories using quantum computers? So if the answer turns out to be yes, it would be great. And if it's no, and also it would be great, because we could think of other type of computers, maybe quantum field computers, in order to like encompass like anything that happens in the nature. So in order to simulate on field theories on a quantum computer, we write algorithms. Algorithms are like this kind of circuits, which we start from some easy to prepare state. We perform some operations on them, and at the end we have some state which represent the state of a system. Here would be a state of a quantum field, and then we can extract the information from the state representing that quantum system in order to get information of the physical observables. Sometimes we have to run this algorithm many times in order to get useful information after post-processing the data. When we are casting this algorithm, we are counting this number of gates as a measure of time or runtime of the algorithm. In some scenarios, which doesn't, yeah, it shows. In some scenarios, some of these gates are very expensive to apply. So we count them, those expensive to apply gates, as the measure of time for the quantum algorithms. But in the case of classical algorithms, we don't count this low-level operation. We count high-level operations. Would be like number of flops that we are doing in one classical algorithm. So when in this time that quantum algorithms are getting mature, we will be looking at the high-level operations as a measure of our runtime. We will be counting the number of high-level operations. And interestingly, these high-level operations are those operations that are very expensive to apply. It would be a very, quantum version of random access machine for classical computing. There are some building blocks of quantum algorithms that are used as a subroutine in many algorithms, or Hamiltonian simulation. In this problem, we are given a Hamiltonian, and what we want to do is to simulate the time evolution operator, which is this operation. To decompose this operation in terms of like basic operations that I described earlier. In order to do efficient simulation, we have to be given this Hamiltonian and efficient way, which are usually they are given by oracles, where the oracles specify the location of non-zero elements in the Hamiltonian, and also the value of those non-zero elements. So we can query these oracles and get these values, construct the algorithm which simulate the Hamiltonian, which would be a subroutine for a larger algorithm for simulating quantum systems. The complexity of quantum algorithms for Hamiltonian simulation scales polar logarithmically with the dimension of the matrix. Also, if you have a error tolerance, it's polar logarithmic in 1/epsilon as well. And it has been shown that the optimal algorithm is scaled linearly with the time, which is the no fast arriving theorem. So this is one of the main subroutine in many algorithms for simulating quantum systems.
Sorry,
yep.
Polynomially with the dimension, or with the number of qubits, or polylog with the number of qubits?
It's a polylog in the dimension of the matrix.
So polynomial and the number of qubits.
Yeah. But classically it would be exponential in the dimension. So for simulating quantum field theory, it follows like the structure of quantum algorithm for simulating any quantum system. We start with qubits in all zero state. We prepare some initial state, evolve the state, and then perform some measurement on the evolved state and get the classical outcomes. We can run the algorithm many times, post-process the classical outcome in order to get the values of some interesting observables related to the system. For quantum field simulation, the initial state generation involves preparing states which represent particles before the interaction. Those are interacting particles. So in order to do so, we typically prepare the ground state of the non-interacting part of the theory, and we go to the interaction regime by adiabatic evolution. We prepare particles of free theory out of the ground state of the free field theory, and then we have free particles. By adiabatic evolution, we would have interacting particles before the time evolution. In the time evolution part, which is a Hamiltonian simulation, it evolves the state of the particles, and the scattering occurs in this time evolution. At the end, we perform measurements on those scattered particles. The measurement could be in the interaction regime, or we can just go back to the free regime and do the measurement on that regime. Typically, we are interested on the momentum of the outgoing particles. So what is measured are momentums of the state representing the particles after the scattering. This is the seminal papers of the Kedigo describing like the typical way of simulating a quantum field theory. So to simulate a quantum field theory, because inherently is a continuum system, we have to discretize it. We have to truncate the space, discretize it, and then digitize each value of the discretized field. Each value of the discretized field would be any number, minus infinity to plus infinity if it's a real field. So in the digitization part, we represent those fields by bits if you're doing classical simulation, or qubits by if you're doing quantum simulation. Discretization by this lattice that we are writing in is a typical way. Alternative way is using wavelets. Wavelets are special functions that you can translate these functions and dilate them and generate a basis for the space of the functions that are the space of the fields that we are working on. Here we have this blue. The blue one is a scaling function. You can translate it, generate a basis, and which would be like a complete basis for the space of the functions that we are working. We can also use scaling functions along with the wavelets. We are the shrink versions of the wavelets. You can generate a multi-scale basis for the space of functions, and then you can use that as a way to transforming a continuum system to a countable system. No matter what way of discretization you use, the ground state remains the Gaussian state for the quadratic Hamiltonian that I described. But the covariance matrix here, the matrix at the top of the exponential, depends on the way that you're discretizing. If you use the lattice-based simulations, the blue one, it would be the figure on the left would be your covariance matrix, square root of the matrix K. The other figure represents when we are using multi-scale wavelet basis. It has this nice pattern that it would be like a bands of a finger. It's called the finger pattern structure matrix.
Can you explain what the axes are, what these plots are?
The plots are, these plots represent the matrix, and the color of the plot represents the value of the matrix. The matrix that we have is the k to the half on the top of the exponential, which is the covariance matrix of the ground state of the quantum field theory, the free part of the quantum field theory. So what we are doing here is just we are taking the inner product of the basis function that we have, or the derivative of them. It depends on the Hamiltonian, and if the Hamiltonian is free, that's the ground state. The K matrix represents the coupling between different terms. If you take the square root of it, with the covariance matrix of the Gaussian state, in 2 dimension, that would be our Gaussian state. And if you diagonalize it, the standard variation of each Gaussian would be encoded in this covariance matrix. Is that the answer? Okay, so when we have this matrices that is coming from the discretization of the fields, if you do the multi-scale wavelet basis, most of the elements are close to 0, and it doesn't depend on the mass term of the Hamiltonian. For any mass term that you use, that would be your structure. If you remove those close to 0 values, you will have like a sparse matrix. And then using the sparsity of the matrix, we can construct an algorithm that is optimal, which I showed. But if you use the lattice space method or fixed scale method, this would be our matrix. It's we can diagonalize this matrix as well efficiently by Fourier transform. It's a circular matrix. And we can construct also algorithm based on that method. So
question. So you mentioned that you truncate, you have a space.
Yeah.
So of course, for the initial state, we can it's clear to decide the truncation, but then you evolve it in time. So how do you know what?
We truncate the space, which is the domain of the functions that we are working with. That's the truncation. But when we are discretizing that truncated space. In the lattice space method, the discretization is the discretization of the domain, but in the wavelet basis, what we are discretizing is the space of the functions. So we are taking countable to
The truncation, and say space, yeah, it's X, yeah, your coordinate was X. So you have
the X here represent the field. So this X could be like phi. Phi is the state of the field. So in the ground state, we have superposition of different field distributions.
Except when you say the field X is a vector, as you're saying K is a matrix.
Yeah.
In all different modes.
Yeah, exactly. It's infinite dimensional, but once we are doing the discretization or truncation, also we have 2 types of truncation. Maybe that's part of. One is this truncation of the space itself, and the other one is truncation of the field, the Hilbert space.
Instead of using wavelets, we have a non-interacting theory, and we just did a usual Fourier decomposition into energy modes, K modes.
Yeah.
Then this root K would just be diagonal, right?
Yes.
So you get a more complicated matrix because of the wavelet decomposition that you would choose.
If you work on the momentum basis, that would be diagonal, but it's not in the momentum basis, it's on the field representation. So even if you use the Fourier basis, it's like we have the phi.
About the different K modes of the field. Right?
Yeah, it would be phi versus the derivative of phi. Derivative phi is the momentum representation, but the phi itself is the field representation. So when we have this Hamiltonian here, like I have to go back. Where is it? Yeah, this Hamiltonian here, we are representing this Hamiltonian in a basis. So what you're taking the inner product of this Hamiltonian with respect to the basis functions. So if you're using the wavelet, it would be like one wavelet function, another wavelet function, Hamiltonian here, take the integral. So it would be like, so you would have a different functions, and if you put them together, it would be a matrix that describes the coupling between different modes. But if you use if you use the lattice discretization or fixed scale discretization, that would be a blue plot. Wavelet would be other plot. If you use the Fourier basis, because you're taking the gradient, everything it becomes diagonal in that basis. Yeah, you're right.
The matrix becomes sparse.
Yeah.
That's specifically because you make a clever choice of this wavelet basis, or you're saying it's kind of a generic property?
It depends on the Hamiltonian. For this point, this kind of Hamiltonian, it becomes a sparse. For complicated Hamiltonian, if you take this one, it's not necessarily sparse. So it depends on the operator that you're representing on the basis.
Sure, but even for the simple Hamiltonian, I'm just asking, is the matrix guaranteed to be sparse?
Yeah, guaranteed to be sparse.
So even if you didn't do the wavelet?
No.
Okay.
If you do the multi-scale wavelet decomposition, it would be a sparse. If you do fixed scale, it won't be sparse anymore. That's the property of the multi-scale, and that's one useful features of the wavelets, that when you're going to multi-scale, it becomes a sparse matrix. What you're doing is like you are representing this differential operators on a wavelet basis, and it has been shown that for many differential operator, this representation becomes a sparse matrix. Okay, so alternatively, we can use the fixed scale basis also, but we have that. We have
Clarify what you mean by fixed scale or multi-scale?
the fixed scale. You just take the scaling functions, translate them, generate a space, which would be a subspace of our Hilbert space. But if you shrink the scaling functions small enough, generating them, you're increasing this the subspace of the Hilbert space that are represented by these functions. So that would be itself alternative way of representing this square integral functions.
So do you end up generating an over complete basis?
Complete basis.
But it's over complete, or it's
No, it's complete basis. It's not over complete like Gaussians. It's not a Gaussian. These are orthogonal functions which generate a complete basis. But it depends on the way that you're generating it, whether if you use the scaling functions or the scaling functions along with wavelets in different scales. It would be different way of characterizing the Hilbert space by using these functions.
maybe, can you actually explain what the axes on those wavelet plots are, and like what's S of X and what's W of X?
Oh, it's coming from the wavelets. Wavelets are defined by two basic functions. They are called scaling functions and wavelet functions. They are not unique. You can use this wavelet, which is the Haar wavelet. You can use the other wavelets when it's specified by one parameter. When you're increasing the parameter, the functions of the scaling or wavelet functions become more smoother, but they are getting wider. So they are not more, they are compact, but the domain of them are getting wider. So it's like 3, and if you go increase it, it would be 5, it would be 7, and you're gonna get like larger. It's not a unique basis. It depends on these functions, but you cannot choose any function. It must satisfy some criteria to be a useful basis for the space of.
And are these like little wiggle edges in the real, or that's just like mathematical decision or something?
For this one, these are not differentiable functions. They are not continuously differentiable functions, but the other one is continuously differentiable function. The wavelet that I use is the latter one, because the derivative that we have is the we need first time differentiable functions in order to exactly calculate the elements of the matrix. But it depends on your application and which wavelet to use. Typically, this wavelet, Dobeschi wavelets of order 3 is used for many applications because of this. They have nice property. But if you go to higher order, it would be more smoother, more differentiable functions. But again, it depends on your application. It's not unique like the Fourier transform. We would have it. Yeah, what we do in generating the ground state is that we take the inputs. The inputs would be the parameter that specified the wavelet, would be like the K parameter. The other parameter specified the Hamiltonian. The Hamiltonian that we are working is just one parameter, the mass parameter, I'm not. Would be like the number of modes that we are working and the error tolerance that we have. So we classically post-process this parameters, compute some parameters that using those computed parameters as an classical input to the quantum algorithms, we generate the states that approximately represent the state of the ground state of the Hamiltonian. What we do basically, we have that multi-dimensional Gaussian state we prepared a bunch of one-dimensional Gaussian state, and then we performed one basis transformation. If we use that fixed scale basis, because we can diagonalize it by Fourier transform, the basis transformation would be like you're efficiently applying the Fourier transform to get the multi-dimensional case. But if you use the wavelet basis and you diagonalize the matrix, but it's not a unitary diagonalization, you bring it to the diagonal form by Cholesky decomposition, and this shear you have to specify, because it's not unitary transform, you have to specify the elements of the matrix. This S matrix are specified, the parameter that is specified at transformation. We take that as a classical input into the basis transformation and map it to bunch of one-dimensional Gaussians to one Gaussians of multidimensional Gaussian state. So we show that like even like classical and quantum parts, the cost is scales close to linearly with the number of modes, and we also show that this is optimal. Any algorithm that is sublinear in terms of the number of modes would generate a state that won't be accurately representing the ground state of the free field theory. So part of it is coming from generating one-dimensional Gaussian state. The method that we use a novel method for it, based on doing some testing an inequality on a quantum computer. What we do, we are doing this kind of transformation where we have 3 registers here. The last register is one single qubit. It's the flag register, and the flag is up when the value of the first register is greater than the second one. Otherwise, it keeps down. And we can do this in superposition on quantum computer. This enables us to prepare some states much more efficiently than the standard methods. Like if we have the Gaussian state, which I have shown like half of it here, the blue line, this is what we want to prepare. But we can prepare a state with that orange line efficiently. What we do, we prepare the orange line, and we map this state with the orange amplitudes to state with blue amplitudes. The way that we do is we compute the ratio of them in another register, and what we want to do is map the content of this register to the G in order to get the F, the blue register. We do this by performing that operation, the inequality testing. So the whole operation that we are doing, the computation that we have here is just computing the one single exponential, which is the ratio of the blue versus the orange lines. Whereas in the standard methods, we have to do like complex arithmetic operation in order to prepare the same states. We remove this arithmetic from the algorithms in order to prepare the same state much more efficiently. Going to beyond the ground state is preparing the free particles. When we are using multi-scale wavelet basis, we have a description of the theory in multiple scales. And we can use this description in order to generate the states representing the particle. For one-dimensional case, this would be a Gaussian state. It's just one single harmonic oscillator. You take the creation operator, apply it to it. You will have one state that represents one particle state. You can go into like change the domain of the function in order to go higher momentum functions, because we have the description in multiple scales. We have the description of this kind of operations. We can apply them and generate them all at the same time if you want. Whereas if you use the fixed scale basis, what you do is like you have to generate this state, do some manipulation in order to go to other states, which adds more cost to the algorithm generating the states of particles. These are non-unitary operation. We do some tricks in order to implement them. And also when we break the translational invariance on the system, we add some terms that are breaks the translational invariance. But even with those terms, the structure of the matrix doesn't change. And the algorithm is heavily dependent on the structure And it also covers the case that we have non-translational invariant field theories. We can generate states of those theories using multi-scale basis. The last part is extracting information from those generated states. So formally what we have a generated quantum state psi. We have given an error tolerance, and we have a measurement observable. And what we want is an epsilon approximation to the this expectation value. The metrics that the observable that we check is general observable. We take it like the oracles, specify the location and value of the non-zero elements. If you use the standard methods, there are a bunch of methods like the Hadamard test, which you just run this simple circuits. You have to repeat this circuit in order to get the information, and the number of repetition depends on your error epsilon. Other alternative way of calculating this expectation value, which depends on Hamiltonian simulation. You do like this kind of tricks. You do Hamiltonian simulation for a short amount of time, and then do some tricks in order to get the expectation value. For all of these methods, the runtime with respect to the epsilon is not linear. The best case is this one, where the tilde represent like when we are ignoring some logarithmic factors out of the cost of the algorithms. What we do, we bypass the Hamiltonian simulations and construct a way to calculate the expectation value, but by calculating amplitude. And the complexity is exactly linear with respect to 1 over epsilon. This is the Heisenberg limits, which applies for general observable. You cannot do based on the Heisenberg limit, you cannot go sublinear. But the way that we prove it mathematically is the optimality of the algorithm is reducing the approximate one problem, which is called the approximate mean problem, to the measurement problem. The first problem is proven to be optimal with respect to the error epsilon. In that case, we have a function given by oracle, and we query the oracle in order to get the average of the functions over the values. The number of queries scales linearly with 1 over epsilon, and that's proven to be optimal. When you reduce it to this problem, we show that this is also optimal. This I should mention that applies for general case. There are cases that we can break the Heisenberg limits, and we can have sublinear algorithm, but this is the best thing that we can do for a general case. So this is what I had to talk about the term quantum computers. So for the last part, I'm gonna talk about the empirical hardness models, which are tools that we can use for predicting hardness or complexity of one algorithm. So we are looking at the average case complexity rather than the worst case complexities that I've mostly described in the first part of my talk.
Question then about the first part. So what types of questions can you address with the method? So you prepare the initial field.
Yeah.
So just when you show, for example, they discuss the experiments, of course there is a collision.
Yeah.
So can you mimic these types of?
Yeah, for general algorithm that I described, it's like it involves Hamiltonian simulation and measurements. The Hamiltonian simulation is already optimal. What we were working on the initial state preparation, because that was the most expensive part of the whole algorithm. So we removed that part to be more expensive. So the entire algorithm now is optimal. But for one class of quantum field theories, not for any like standard models. It's just the simplest quantum field theories. But yeah.
But then what types of questions can you address with this tool?
It would be like a scattering process, simulating a scattering process in quantum field theories, measuring momentums of the outgoing particles, or any other things that we are relevant to quantum field theories. These are the questions that we can address by quantum simulations.
Is it being done?
Yeah. That's the first part of the Hamiltonian simulation or the measurement. There are algorithms for doing it. The state generation part was the most expensive part. We removed that part, but for another type of quantum field theory, you have to devise like is quantum field theory dependent. But for particular class of field theories, you can do all of this operation and calculate some, expectation value, some observables related to field theory. But mostly, what has been done is calculating, simulating a scattering process, and also calculating some expectation value related to quantum field theories.
When you say what's been done, you mean what people have designed algorithms to do, not
Yeah.
what's actually been implemented on a quantum computer.
No, these are, far future thing, which are, theoretically show that by quantum computers, you can simulate this type of quantum field theories.
So I guess what I'm curious about is how far do we have to get to actually see quantum advantage for quantum field theory calculation? How many good qubits would you need?
In order to do the simplest quantum field theory that I
We could do something faster than we could do it on a classical computer. This is exponential on the classical computer. That's the issue.
yeah. In order to do it, I've just with a rough estimate, I've constructed a method that it requires 1,000 logical qubits in order to like very simple calculations, and also with not so accurate calculations.
But you think already a calculation that would be hard classical?
Yeah, it would be hard classically. Those, we can do those, but it's like more, as I said, for simplest quantum.
That's not good.
1,000, if you have 1,000 logical qubits, perfectly functioning operators, then we will have we would be doing something that we cannot be doing classically. But that something might not be something that is useful or describing something very important. Yeah, but we are very far away from simulating a standard model of like this type. So for the empirical hardness model, so we typically, when we are considering problem, the hardness of the problem. Yeah.
Yeah, so I'm just wondering about the classical hardness of it, because it seems like you already know, like, you don't know the exact eigenstates, but you know as far as representation already.
Yeah.
So is it clear that you could make a classical algorithm that takes advantage of that sparsity, do some kind of perturbative?
Yeah, the issue is that we want to generate a state even for like 40 qubits. The space, the memory that we need to store that 40 qubit would be more than 4 terabytes. So if you make it 41 qubits, like exponentially exploding space that we need to represent the field. So it's just stuck in the representation, not alone to go to the simulating the dynamics or even.
The representation you're talking about, so like you could position your basis representation,
It doesn't matter. It doesn't matter what representation that you're using, but if you want to generate the ground state on a bunch of qubits, the memory size that you need to represent the states is exponential with respect to the number of qubits. So,
so even though the matrix is sparse, you're saying the number of elements that I need to keep track of in the matrix is still growing exponentially.
Yeah, that's the issue.
Slower
Yeah, that completely answered. But
okay.
if it's, shall I continue? Okay. So for hardness of a problem, we classify the problem based on their hardness. There are classically easy problems or quantumly easy problems, but there are problems that are hard even for quantum computers. There are examples of it, like traveling salesman problem. When you are a bunch of cities and you're looking at a close path in this city that visits every city and has the shortest path. It's a widely studied problem in classical setting. It also applied to monkeys that mimic the traveling salesman thing. It's been studied for centuries, and there is no efficient algorithm for this type of problem. The other one is satisfiability problem, that you have a bunch of different clauses and you want to satisfy all of them. Specifically, if you look at the 3-SAT problem, where the size of each clauses is 3, that would be NP-complete problem, which are the class of the very hard problems in, for any type of the algorithms. For larger clauses, you can map it to 3 sets. So for these are the parts of this very hard problems. And there is no efficient algorithm for them. They are widely used in applications for different industries. There are people constructed algorithms for solving this thing. But when we are considering this efficiency of this algorithm, so the main question that we are answering in the empirical hardness model is how hard is it to solve a given problems in practice using the best available algorithms that we already have for this type of a problem. Clearly, the theoretical analysis is hopeless here. For example, if you look at this here, we have 500 nodes. And if you look at the traveling salesman problem for this randomly generated 500 nodes, it wouldn't be, by theoretical analysis, we wouldn't be able to solve it within our lifetime. Whereas I'm going to run one algorithm, which is looking at, it's not running, but but there is like an algorithm that looks at the traveling salesman on this graphs. It takes only 5 seconds to solve it. And I didn't use.
Solve it approximately or solve it
exactly 5 seconds. But if you change the problem, it's not going to be 5 seconds. It might be 10 seconds or 15 seconds. I didn't use a special tool. It's my finicky laptop, 7-year-old laptop, lowest spec. It took 5 seconds. It depends on the solvers that you're looking. There are 2 competing solvers for traveling salesman problem. The first one can exactly solve with bounded size problem instances of close to 86,000 nodes. There is one heuristic algorithm that solves this problem for a node of 110,000, that size. What we see, if it didn't show here, but if I run this algorithm again for different problem instances, it wouldn't take like second. It could take like longer time. So what we have is competing algorithms for solving the same problem is that first, it doesn't have any theoretical guarantees that to have exact solution. Although for bounded size problem, there could be algorithms like the Concordia that I've shown here. It is exact. It works surprisingly well in practice, like the example that I showed here. And also, the performance of this algorithm varies a lot. It could take a few days or few months or few milliseconds to solve the same problem that theoretical analysis shows that you cannot solve it efficiently.
Just to make sure I understood.
Yeah.
You're saying a generic problem like this would take our lifetime to solve, but specific instances happen to work quickly on this.
Yeah.
This one took 5 seconds, but you chose this one because you got lucky.
Yeah, so it highly depends on the problem instance. If I change the position of one of these nodes, it wouldn't take like seconds. It could take few days, could take like a lifetime. But for many, not specifically for this, because the Concordia has been shown that it's exact, but it's for bounded size problem. But for general problem instances, it's not the case. It's exponential. So in the empirical hardness models, what we are looking at the models that predicts the performance of those algorithms for given problem instance distributions. It has a bunch of steps. The first steps is you select one algorithm among a set of competing algorithms for solving the same problem. The second step is selecting a problem instance distribution. When you have a different problem instances, you're selecting a bunch of them, like graphs of size 500 to 1,000. That would be your problem distribution. You're identifying a set of features or parameters that characterizes your problem. The features must have 2 main properties. This must be fast to compute, much faster than the problem itself. It must be informative in the sense that it must correlate with the performance of the algorithm. If it's easy to solve problem, the feature must tell us. And if it's like a hard problem, it also distinguishes between easy to solve or easy to prove that it's not solvable versus the hard to solve problem instances. You're generating the data for this problem distribution that you have, and then at the last step, you're learning a model which predicts the hardness of your problem. Typically, is runtime. where you have the actual runtime of the algorithm versus the predicted runtime of the algorithm. It's empirical in the sense that you have to run the algorithm to get the empirical results and then construct a model that predicts the performance of the algorithm for new problem instances. Sorry.
So what are the arguments of this?
Oh, this is actual hardness of the problem versus the predicted hardness by the model. Hardness is the thing that we care about. It would be runtime, it would be accuracy of the algorithm, it could be any other parameters that we have. So we looked at one of these problems, the Hamiltonian cycle problem, closely related to a traveling salesman problem. What we are given a graph, looking for a closed path in this graph that visits every node only once. And the question that we have is how long does it take to find the Hamiltonian cycle for a given graph? The problem instance distribution that we took is specific graphs, cubic graphs, where the graphs with nodes 3 have nodes of 3. And the number of nodes is between 300 to 1150. We took the Concordi solver. We put the cap time of 10 seconds for that solver. So we're looking at the problem instance distribution that can be solved within 10 seconds with that solver. We overall, after around 70,000 problem instances, we excluded this cap data from the all data points. At the end, we have 40,000, close to 40,000 problem instances that can be solved within 10 seconds with that solver. And we constructed a model that predicts the performance or runtime of the Concordi for this set of problem instances that we have considered. As you see, it has a high Pearson correlation values. So
it looks from this plot, like as you go to harder problems or longer runtimes, the actual runtime is almost always shorter than the predicted runtime. Is that just an artifact of like not letting it run long enough or something? Just for the easier problems, you don't see that, right?
Yeah, it highly depends on your problem instances. We have excluded those runtimes as taking longer than 10 seconds. But if it's like the larger portion of the data,
right, and almost everything is below the red line.
Yeah.
So on the left, it looks like it's often harder than you predicted. On the right, it looks like it's always easier than you predicted. Is that real, or is that because something's been left out of these plots?
I'm not sure about this to answer to this.
Seems shocking.
Yeah, but it's like it has, as you can see, it's like pretty good model to predict the performance of the algorithm for a given problem instances. So if you have a new problem, you can use this model in order to predict its runtime. And also it's log of the runtime, so it's for.
It looks like it's overestimating the runtimes by a factor of 10 to 100. Right. I'm just
Oh, okay. Maybe I need to take a closer look at this this problem, but yeah, that's one application of the empirical hardness models, is that when you are given a problem, you construct an algorithm analyzer that analyzes its hardness based on this modeling. And the other one is when you have a set of algorithms for solving the same problem, you can use the empirical hardness model to select the best algorithm that solves that set of problem instance distributions. It would be like algorithm selector, like a meta algorithm for choosing the best algorithm. The last application is configuring the parameterized algorithms. When you have an algorithm that depends on so many parameters, with respect to some problem instance distribution, you can tune these parameters using empirical hardness model that applies for that set of problems and chooses the best parameters for that problem. So it's just the final minute, and just our vision for quantum case, which is a work currently being done. What we want to do is apply empirical hardness model to configuring the near-term algorithm, which is mostly parameterized quantum algorithms. And we will be looking at the parameters that makes the algorithm to perform well for particular problem distributions. We can also make a quantum meta algorithm that selects the best algorithm among a set of quantum heuristic algorithms for particular problems that we have. Also, there are problems, there are characteristic of features that you cannot calculate them efficiently classically, but if are like some correlation functions that you can calculate them efficiently in quantum computer, we can use them as a feature for classical imperial hardness models. And the final goal is to construct purely quantum imperial hardness model to predict performance of the quantum algorithm for different things. The end, thank you for listening. Also thank many people that were involved in this different things that I mentioned and different funding agencies. Thank you.